Welcome to Spring LIB.
This is chapter 37, problem number 70. This is where we show that the wave equation is not invariant under Galilean transformation, but it is invariant under Lorentz transformation. So this is going to be a long one, so sit tight. So let's start with part A. First of all, we're given the wave equation, okay? The wave equation goes, the second derivative of the electric field with respect to x is n minus 1 over c squared. Second derivative of E, again, it's depending on x and t. Time derivative this time equals to 0. This is our wave equation. And with the Galilean transformation, we're given the wave equation in terms of, instead of derivatives with respect to x and t, we're given with respect to x prime and t prime. As you can see in the problem, the wave equation looks very, very different. That's why we're going to show that this violates the Galilean transformation. After we apply that, it violates the postulate, the relativity postulate here, because it doesn't have the same form. Now, how are we going to apply the Galilean transformation to this is then the question. Now, we know if we want to go to x prime via Galilean transformation, what we have is x minus vt, right? For the time, it would be the same, right? We don't have a change in time. So let's assume that we have a function, okay? This function depends on x and t. And we have our x that depends on x prime and t prime, because that's the case here, right? And the time function that depends on also x prime and t prime. So then any function that is depending on x prime and t prime could be actually written as f(x), but also depending on x prime and t prime, and time that depends on x prime and t prime, right? We're laying the foundation for the derivatives now. Now, if you want to take the derivative of this function f that depends on x prime and t prime with respect to x, for example, then what we're going to do, we're going to do the chain rule, right? So the f over dx prime times dx prime over dx plus df over dt prime t prime over dt. Well, hold on, df over dx prime dx dt prime. Sorry, this is supposed to be x, right? Sorry, apologize. This is x. Now, if we take the time derivative of this function, I'm going to put it here, df x prime t prime dt, right? On a separate note, we have df over dx prime dt, right? Plus df over dt prime dt. Now, we know, let me go to the next page. We know that x prime from the Galilean transformation equals x minus vt, and t prime equals t. So dx prime over dx is going to be equal to 1, right? From the first equation. As far as the first, let's call this the first equation. Let's call second equation. Based on the first equation, I was talking about this term, and I'm going to determine what this term is. And I'm going to determine what this term is and the other one. Now, going to the second page. Again, this comes from the first, labeled as first equation. And there's also dt prime and dx over there. As you can see, dt prime dx is going to be equal to 0 from here. As far as the second equation is concerned, the x prime over dt is going to be equal to negative v, right here. And we also have dt prime over dt, which obviously is going to be 1 from this equation. Now, all we need to do is to go back to, let's say, df over dx equation. We said that it was df over dx prime. Now, instead of dx prime over dx, it's just dx prime over dx is 1. I'm plugging it in the first equation. Again, I'm rewriting the first equation. Then the second term, because dt prime over dx is 0, the second term drops. So all we're left is actually this equation from number 1. From the second equation, if we plug this information in, df over dt, if you remember, equals to df over dx prime, and then the second term here was dx prime over dt, this term, which is negative v. The second term was plus df over dt prime times dt prime over dt. Dt prime over dt is 1, so I'm not putting anything here, any term here. It's just 1, so it's itself. This is what has become of the second equation. So if we can write it nicely, maybe negative v df dx prime plus df dt prime. Now, in the wave equation, we always have the second time derivatives and second derivatives with respect to x. So we're going to have to take derivatives of these equations again, right? So first of all, from now on, we can call our function as the field itself, right? So let's rewrite the first equation. dE over dx then equals to dE over dx prime, okay? Now if we want to take another derivative of this, dE dx squared then is going to be equal to dE dx prime squared. This is very important. We're going to need this later. Now, the second equation, though, the derivative of it is not that straightforward because we have two terms, as you can see here. But let's write it in terms of e. dE dt equals negative v dE over dx prime plus dE over dt prime. Now, if we want to take the time derivative of dE over, this entire equation, number 2, I'm going to go to the next page. So we have an additional dE dt here, and then we want to take dE over dx prime. From the chain rule, we're going to have to do the chain rule. This is going to be equal to dx prime over dt, d squared e, second order, and prime squared, plus dE over dt prime, dE over dx prime. Now this is going to be equal to, again, the x prime over dt was negative v. So the second derivative again, x prime plus square e over dt prime and dx prime. And now if we take time derivative of the other term, dE over dt prime, what we have is dx prime over dt, dE dx prime dt prime plus dE dt prime dE dt prime. Now we know that this is negative v again, so negative v dE x prime dt prime plus the second order of the derivative of e with respect to t prime. Now let's go back and rewrite dt over dE dt then is going to be negative v 1 over dt dE over dx prime plus d dt dE over dt prime. Well, we just calculated what these guys were, right? Plug them in here. We said that this term equals to negative v d squared e over dx prime squared plus dE second order dt prime dx prime. We said that this term equals to negative v dE squared dx prime dt prime plus second order t the delta dt prime squared, and the left hand side obviously is going to be dE squared dt squared. So then plugging everything in, this term multiplied by negative v, we're going to have v squared d squared e over dx prime squared, and then we have the second term times negative v, so negative v dE squared dt prime dx prime. Then minus, we have the second term here, minus v dE squared over dx prime and dt prime plus d squared e over dt prime squared. Now, as you can see, these two terms are repeated, so let me rewrite it. V squared over d e squared over dx prime squared minus 2v e squared over dt prime dx prime plus d squared e over dt prime squared. And as you know, we also, so this is d squared dt squared. An important equation here that we're going to need to plug this in the wave equation. Remember, he had also found that part was not that problematic. The second derivative with respect to x of the field equals to second derivative with respect to x prime squared. Now we're gonna basically take these two equations and put them back in the wave equation. So when we do that, what we have is dE squared dx prime squared minus 1 over c squared, right? Not forget the coefficient v squared dE dx prime squared minus 2v dE squared dt prime dx prime plus d squared e over dt prime squared. This equals to 0. Again, we have two terms that contains derivative with respect to x prime. We can combine those, right? So we have then 1 minus v squared over c squared dE dx prime squared. And then we have the second term times negative 1 over c squared. That would give us plus 2v over c squared dE squared over dtx dx prime. And we have negative 1 over c squared dE over dt prime squared equals 0. As you can see, this is the same exact expression that we have. So we found the wave equation under Galilean transformation. So this would be our answer to part A. Now, going to part B, we're going to pretty much do the same thing. Same logic, only this time when we're taking the derivatives, we're not using the Galilean transformation. Now we're doing this under Lorentz transformation, right? And we're going to show that the wave equation has the same exact form as we know it. So remember, for the Lorentz transformation, we have the x prime equals x minus vt times gamma. And for t prime equals gamma t minus vx over c squared. Now, I'm not going to repeat the entire steps because it's going to take a long time, but at least let me tell you how it's different than part A. So first of all, the first derivative is gamma here. So the x prime over dt is going to be negative v gamma, and dt prime over dx is going to be negative gamma v over c squared, and dt prime over dt is going to be gamma again. Using the same logic, dE over dx equals dE over dx prime, dx prime over dx, again the chain, using the derivative, dE over dt prime over dx. So this is dE over dx, what it equals to. Again, let's remember that this term, we found it out to be negative gamma v over c squared. We found this term to be gamma. So we can actually rewrite that equation as dE over dx equals dE over dx prime gamma. Let's put gamma here. Minus gamma v over c squared dE over dt prime. So this is going to be used later, so let's leave it here. Now if we do the same for dE over dt, what we have is negative v gamma. Well, okay, let me not skip that part. Let me explain you where that comes from. Again, dE over dt equals to dE over dx prime, dx prime over dt, plus dE dt prime over dt. Now, dt prime over dt, where is it? dt prime over dt is here. It was gamma. So this term equals to gamma. Well, how about this term? The dx prime over dt. Dx prime over dt is negative of v gamma, right? Negative v gamma. Now, if we rewrite this equation, then dE over dt equals to negative v gamma dE over dx prime plus gamma dE over dt prime. Again, we're going to use these two equations. We're going to take the time derivative and derivative with respect to x again, and then the method is the same, and then we're going to put the second order derivatives in the wave equation. So the second order, I'm not going to openly write the chain rule again, but the second with respect to x is going to be gamma squared d squared e over dx prime squared plus gamma squared b squared. This is a squared. B squared over c to the power 4 d squared e dt prime squared minus 2 gamma squared v over c squared d squared e dx prime dt prime. Now let's look at the time derivative dt squared, right? It's going to be gamma squared v squared d squared e dx prime squared plus gamma squared d squared e over dt prime squared minus 2 gamma squared v d squared e over dx prime and dt prime. This is dx prime times dt prime. Now, all we need to do is to put these two equations in the wave equation. You know that in the wave equation, you have the derivative with respect to x first, and then you have minus 1 over c squared times this term. So that's exactly what we are going to do. So let's start with the first term, right? So gamma squared d squared e over dx prime squared plus gamma squared b squared over c to the power 4 squared over dt prime squared minus 2 gamma squared b over c squared d e squared over dx prime dt prime minus 1 over c squared. This was the term that I was warning you about. Then we have this term, right? de over dt squared. Now we have gamma squared b squared second dx prime squared plus gamma squared d e squared dt prime squared minus 2 gamma squared b de dx prime d t prime. Now, we have these two terms that are the derivatives based on x prime. So coefficients, let's group the coefficients. So gamma squared, right, minus gamma squared b squared over c squared. This is the coefficient of d squared e over dx prime squared. Now we grouped these two terms. The second term is depending on t prime. So this term and this term, right? This term. Now let's look at the coefficients. Gamma squared b squared c to the power 4. And then what we have here, negative of gamma squared over c squared. This is d squared e over dt prime squared. The last term we have, let's put minus here, we have 2 gamma squared v over c squared minus 2 gamma squared v over c squared. Okay, this is going to cancel out this term. d squared e over dx prime dt prime. This is going to be equal to 0 because we're writing the wave equation, right? So now this term is 0, making this entire term 0. So the mixed derivatives, the term that has the mixed derivative is gone. So we're left with this part. Let me go on a new page. So gamma squared minus gamma squared v squared over c squared d e squared dx prime squared plus gamma squared v squared over c to the power 4 minus gamma squared over c squared d e squared over d t prime squared equals 0. So now let's take gamma squareds out. Gamma squared 1 minus v squared over c squared d dx prime squared plus gamma squared v squared over c to the power 4 minus 1 over c squared d dt prime squared equals 0. So if we divide each term by gamma squared, nothing happens to the right hand side. It's still 0. So we're getting rid of these two terms. Now we're good. As far as the first term is concerned, it looks like the wave equation. However, let's see the second term. Let's see what this term equals to, okay? So v squared over c to the power 4 minus 1 over c squared is what we have. And if we divide the v squared over, let's just equate the denominators so that we can do the algebra. V squared minus c squared over c to the power of 4, and we have a gamma squared in denominator, right? Well, so this term equals to v squared minus c squared over c to the power 4, but then when we divide both terms by 1 minus v squared over c squared, so we can do the same. So when we rewrite it here, 1 minus v squared over c squared, we don't want this term either, right? Sorry, I got paused for a second there. B squared over c to the power 4 minus 1 over c squared dE dt prime squared equals 0. So now I'm going to divide both sides by this term. Then we're going to see that these are going to cancel out. Now I'm going to try and figure out what this entire term is. Now, v squared over c to the power 4 minus 1 over c squared divided by 1 minus v squared over c squared, right? This is what I'm looking for because this is the coefficient of the t prime squared, the derivative that depends on the t prime. Now, as we work that out, it's going to be v squared minus c squared over c to the power of 4 divided by 1. Well, let's while we're there, let's equate the denominators through here. So it's going to be c squared minus v squared over c squared, right? So v squared minus c squared over c to the power 4 times the c squared over negative would be v squared minus c squared, right? Because if we redistribute, we're getting this term. I only did this to show you that these two cancel out. C squared cancels out. So 1 over c squared is actually that coefficient in front of the second derivative of the e with respect to the t prime. So if I'm rewriting my wave equation based on this equation, so I have only this term left, and this coefficient is 1 over c squared. So I can rewrite it as d squared e over dx prime squared minus 1 over c squared e over dt prime squared equals 0. And this is your wave equation, and this shows you that the wave equation is invariant under Lorentz transformation.